Hello, Kev Hopayan. Today we're going to look at an aspect of evidence-based practice that frightens some people, but there is no need to fear. We're going to be looking at numbers and statistics, but using techniques that you learnt at school, namely subtraction, division, multiplication, and multiplication by 100 to get percentages. We've already looked at how to appraise a paper for validity. Today we're going to look at how to appraise the paper for its importance. Let's just remind ourselves what we mean by that. Importance refers to the size of the effect or how clinically significant the results are. The size of the effect being the difference between groups in outcomes. Validity was to do with the design and conduct of the study and its quality. We've already talked about appraisal, starting with the question, is it worth closer scrutiny? We've answered yes. We've appraised the study for its validity. We now want to know, how important was it? How large was the size of the effect? And to do that, we need to learn some what we call summary statistics. These are numbers that express the size of the effect. And I'm afraid there are several, but let's go through them. And you'll see they're not quite as frightening as you might otherwise have thought. Now, we're going to start first of all with those types of study that report results as proportions. For example, one group may be given a cholesterol-lowering drug and another placebo. The size of the effect would be the difference between the proportions in one group and the proportion in the other group. Okay? Now, the proportion of people in a group who suffer or experience an outcome or event is called a rate in evidence-based practice. Though strictly speaking, in science, as a rate implies a measurement over a period of time. Just to simplify things, we're going to use some symbols. Blue will be for the exposed group and green for the comparison group. Hatched boxes will show those who have had the outcome that we're interested in. And as far as my ability is possible, the size of the box will reflect how big the groups are. Now, this is what happens in a study of interventions. We start first of all with the population that we're interested in. Say this is a group of people who are receiving primary prevention for heart attacks. We take a small sample from that population, let's say 100, and enter them into a study of cholesterol reduction, let's say through the use of statins. We divide this sample into two groups. Here they're equally sized. One is the exposed group, they receive the statin. The other is the comparison group, they receive the placebo. Now, what we do, we look at these groups and we follow them up over a period of time, during which events will happen in each group. Now, the word outcome and event are frequently used interchangeably. We see here that in the exposed group, 10 people have had the event, and in the comparison group, 15. We're going to convert those into rates. Here we are summarizing the flow of patients through the study. So we said 10 out of 50 had the event in the group receiving statins and more 15 in the other group. So how can we express that? Okay, first of all, we take the number who had the event, we divide by all those in the group, and we do the same for the comparison group. This gives us two event rates. For the group receiving statins, we refer to that as the exposed event rate, EER. For the group that had placebo, the comparison, we refer to those as the comparison event rate, CER. And some very simple maths will show you that the EER is 20% and the CER is 30%. Hang on to those numbers because we now use them to show the effect sizes, the so-called summary statistics. The first of these is what's called the risk difference. Difference, you may remember from maths days, is what's left after you subtract one thing from another. So if we subtract the EER from the CER, we get 10%. So the risk difference in this case is 10%. I must just add that in some books you will see this referred to as the absolute risk reduction, which is okay if the outcome is something to be avoided, as in this case we were trying to treat patients to avoid a heart attack or a stroke. But sometimes the risk difference is something that we want, such as the cure rate of antibiotics for pneumonia, in which case you have to use a slightly different word, absolute risk increase. So I prefer RD, or risk difference. Often when you look at published papers, you will see the results are in two columns, the number that have had the event and the number that were in the group. And of course, if you like mathematical annotation, you can think of the event rates as being little n, the number having the event, over big N, the number in the group. And the risk difference will be, of course, the difference between these two numbers. Now we're going to move slightly to a different concept, the number needed to treat, but it is, again, very simple. Telling people that there's a 10% chance of reduction in your chances of having a heart attack if you take this drug is sometimes difficult for them to appreciate. People find natural numbers easier to grasp than percentages. And so the number needed to treat is a method of giving them a natural number. It's defined as this. It's the number of people who would need to have the treatment over a period of time so that one additional person would benefit. For example, by a reduction in an adverse event or an increase in a beneficial one. It's very easy to calculate. It's the risk difference, which we've already learnt to calculate, turned upside down. We can also have a related concept, such as the number needed to harm. For example, the number needed to treat to reduce heart attacks in secondary prevention may, for example, be 30, but the number needed to harm, that's to say those who suffer side effects such as muscle cramps, are probably more over 100. So let's just see how we can turn that into an easily understood form. If you remember, this is how we calculated the risk difference. Now we take the risk difference, which is 10%, and we turn it upside down, which in mathematical notation, you'll remember from school days, is 1 over the number. Yep, that's how you do that. Now, if we start with 10%, then that's 1 over 10%, 10 over 100, and that which works out at 100 divided by 10, which is 10. I come back to the fact that what we're referring to, though, are not true rates, they're frequencies or proportions. When you express an NNT, make sure that you also take note of the period of time over which it happens. When the UK PDS diabetes study was published, there was a lot of confusion in the press between those who quoted the NNTs for the whole duration of the study, with a mean follow-up of 10 years, and those who quoted NNTs per annum. If you see below, a risk difference of 1% over 10 years means a risk difference of only 0.1% each year. That's why it's important to use PECOT with a T to remind ourselves. There's still another way of expressing the size of the effect, and that's the relative risk. It's also known as the risk ratio. Now, this is the ratio of the risk or event rate or probability. Forgive me, all these three things mean the same: risk, event rate, probability. It's the ratio of the risk or the event rate of the exposed group to the risk or the event rate of the comparison group. In other words, RR equals the exposed event rate divided by the comparison event rate. RR equals EER over CER. Let's see how this is calculated. We go back to our two groups. We've calculated the event rates by dividing the number who suffered the event by the number in the group. And we've ended up with these two event rates, 20% and 30%. This is the EER and this is the CER. The relative risk is very easy. It's just one divided by the other. And in this case, 20% divided by 30% gives us that number there. The final one, the relative risk reduction. This is the reduction in risk expressed as the risk difference relative to the risk in the comparison group. Now, that might sound a bit of a mouthful, but let's just think about it. In our group receiving statins, before they received a statin, they would have had the same risk of a cardiovascular event as the control group. You might like to think of that as their baseline risk. When we give them the drug, the statin, we reduce their risk by a certain amount as a result of the drug. That amount is the amount of benefit they have had compared to what would have happened to them had they not had the drug. It's a little bit like if I said to you, if you were earning, say, £100 for a period of time, I said, I'm going to give you £15 more, your relative change in income is 15%. Or if I were being particularly nasty and I took away £15, your relative wage reduction would be 15%. So let's just see how this one works out. We start with the risk difference and we simply divide it by the CER, comparison event rate. But remember that this is the event rate that would have happened to the group had it not received the statin. Okay, why? I can't see you, but I suspect many of you are asking this question. Researchers are free to report the results as they wish, so we have to be able to adapt to them. There are some important differences in their uses, though, and also how we choose to express our results can affect the psychological impact on the person receiving them. This is especially true when we talk about risk difference and relative risk reduction. You'll find a discussion of this in Chapter 2 of your course book. Now, research gives us estimates of the effect of treatment. And by estimates, I mean it tells us what happened in that sample, and we hope that those estimates are close to the truth in the whole population. We'll discuss how precise estimates are in the next session. But just for now, remember that the size of the effect can be expressed by several summary statistics. I hope you found that the maths is quite easy. The concepts, well, you just have to practice them to learn them. So for further work, read Chapter 2 of your course book and practice some calculations on the imaginary study, the Kant study that we've put up online.